Good morning to all. I welcome you all for the fifth day of the GION-sponsored workshop on advances in biofuel and bioenergy research. I would like to introduce Dr. N. Samsudin sir to deliver the talk on the title Bioelectrochemical Systems, Sustainable Technologies for Energy Generation and Wastewater Treatment. Dr. N. Samsudin sir is an associate professor in the Department of Chemical Engineering at NIT Trichy. He received his petrochemical engineering degree from the Bharatdasan University. He did his master's from Anna University and doctorate from NIT Trichy in the year 2016. He also holds the post of the Associate Dean in the Research and Consultancy. His core areas of specializations include the microbial fuel cells, bioenergy, wastewater treatment, and biohydrogen. He was awarded the Young Faculty Award in the 2016 and the BACER Fellowship in 2017. In 2022, he was also recognized with the Best Faculty Performer Award, NIT Trichy. He has attended 25 conferences and published 70 articles.
Go ahead.
He delivered 18 invited lectures and served as a course coordinator and organizing secretary for workshops and conferences held at the national and international level. He has various academic and administrative responsibilities. Ongoing research and development projects include the development of the graphene-based nanomaterials for the bioelectricity generation through tannery wastewater treatment using microbial fuel cell, and sustainable electricity production in industrial wastewater using bioelectrochemical systems, MHRD. He is a member of the International Association of the Engineers, IEI, AICHE, and the Institute of the Chemical Engineers as a life associate member. Let me now request to take over the session. Thank you.
Thank you. Research cricket. Wait. I connected this one. Okay. Try again. It's okay. Fine. So you can give the video to them, online participants. Okay, we will start now. Just to share the screen, if possible. Okay. You can open this. நான் பண்ணிக்கிறேன். Okay, so very good morning to all of you. Sorry for the nearly 40 minutes we have delayed. Okay, so it's not actually suddenly it happened. Okay, so power problem. So already we have mailed to the our administration. So uninterrupted power supply must be given today and this whole week. But unfortunately it happened. Okay, so anyway. We'll give this video to the online participants as well as you also if you need. So, so last 4 days we have I think Dr. Ramaraj Bubadi talked about only the biotechnological aspects for the biofuel production as well as the wastewater treatment. So, and next these 2 days will be mainly bioelectrochemical technology for the biofuel production or bioenergy productions. Okay, so in which the first topic is bioelectrochemical system. So it is one of the sustainable technology for the energy generation. At the same time, it is also going to treat the wastewater. So my presentation talks about three topics. One is what is basics about the what is bioelectrochemical system. That's the first topic, and the second one is what are the factors affecting the bioelectrochemical systems. So if I have time, then I will talk about the what will be the various types of bioelectrochemical systems. So here what I am going to talk again in this so basic fundamenta and followed by what are the experiments we have carried out in my research lab. Okay, then what is the output we got it, and accordingly what kind of the work you can carry out, you can take the input from this, that we are going to discuss today's sessions. Okay, as you know this, we are facing lot of problems in the society. Okay, like we are facing that energy demand as well as environmental issues. Okay, as you know this, we are mainly depends on the different energy sectors. Okay, like our energy sources. We can say either the fossil fuels or gasoline or something the natural gas. Okay, it mainly depends on these three factors. Okay, like as I said. Okay, like natural gas, or we can say it's a fossil fuels. Okay, so we cannot depend on upcoming next 50 to 70 years. So we need to find out the alternative energy sources. Okay, so nowadays we are using that energy sources from only the fossil fuels. Okay, so we are getting the energy, but where that energy is going to? Okay, that energy going to there will be a three sectors. One is we can say two sectors. One is that industrial sector and another one is a domestic purpose. Okay, so what are the energy we are generating from the different sources like wind, thermal, geothermal, or hydrothermal, whatever it is. Okay, it's everything is going to only the two sectors. One is industrial and another one is domestic. Okay, so major the energy utilizing sector will be only the industry. Okay, so industries are utilizing nearly you can see nearly 70% of the energy they are utilizing industries. Okay, only 30% of the energy is going to only domestic purpose. Okay, like household applications. Okay, so particularly if you see it like industrial sectors. Okay, using this energy, and so even if they are using the energy, they are creating the pollutions to the environment. Okay, they are creating a lot of pollutions to the environment. Like if you see it, they are in particularly industry. Okay, if you see it, they are using that energy for these two purposes. One is it is for their particular production process. Okay, One is production process and the second one is a treatment process. Okay, so mainly if we see again they are using that energy for the majorly if we see it like treatment process. So here industries are using the different treatment process. Okay, as you you may be aware of that. There will be a three different process. One is primary treatment process, and second one is a secondary treatment, and third one will be is a tertiary treatment process. Okay, so we can say it's a primary treatment means it will be the physical process, and the secondary almost it will be the chemical process, third will be it is a biological process. Okay, if you see it here, it is primary treatment. Okay, primary treatment means it is only is a physical treatment process. Okay, so your physical treatment means like removal of, okay, as you know this we are having the aqua guard in your in your house. Okay, what is doing in that? Okay, just what the first step will be it is a filter, that sand filter will be there. Okay, so what is the need of sand filter? It is a remove some kind of the sand or impurities. Okay, impurities will be available in the water. Okay, that is filter. Okay, like this here the first one will be is a screening. Okay, screening is the one of the important. Okay, screening, filtration or centrifugal separation, or we can say it is a physical treatment. Okay, physically how to remove some kind of the known, okay, some kind of known or visible material. Okay, if it is available in the wastewater, that we can remove it. Okay, that is the first process. Second one will be it is a secondary process, or maybe it may be the chemical process, or we can say it is a second one. And a chemical process means it will be like what I can say, so removal of flocculation or electrocoagulation process. Okay, via this we can remove this kind of the like secondary pollutions. Okay, secondary process method. And third one will be is a tertiary treatment. Okay, so tertiary treatment is mainly based on either the anaerobic treatment process or aerobic treatment process or activated sludge process. Okay, so via this sludge process we are removing all kind of the contaminants. Okay, from the wastewater. Okay, this is the process how it takes place in the industries. Okay, like first one is a primary treatment, and this is secondary, and followed by it is a tertiary treatment. Then via this we will get is a treated water. Okay, treated water. So here if you see this industries are utilizing, okay, utilizing the most of the energies. Okay, like in terms of electrical energy, utilizing for the only the treatment process as compared to the is a production process. Okay, so any industries if you take it, okay, it will be like this. So like this is one of the technology that is called bioelectrochemical systems, or we can say it is a we can call it as microbial fuel cell. Okay, either the bioelectrochemical systems or microbial fuel cell. Bioelectrochemical system is nothing but it is a one of the device, or we can say system, so which can convert the chemical energy into the electrical energy. Okay, so this concept will be similar to it's a fuel cell concept. Okay, then what is the difference in this? So fuel cell and fuel cells are batteries and bioelectrochemical systems, all three are same concept, that is the electrochemical process. Okay, depending upon the application or depending upon the process, we can say it is either the battery or either the fuel cell or either the bioelectrochemical systems. Okay, so it's a battery, we can say. Okay, you would have seen in your mobile phone or somewhere. Okay, a mobile phone or anywhere, if you would have seen this. So battery, it will be the closed system. Okay, so in all the electrochemical system, we will have the two sides. One is the positive side, another one will be the negative side. Okay, so either positive side we will call it as anode, negative side we will call it as cathode, or it may be depending upon that. Okay, it will be this. So one will be the positive side, another one will be is a negative side. Okay, so in that battery, if you see it, okay, so it is everything is packed. Okay, one side if you see it in the wall clock, if you see the battery, so one side will be some knob will be there, that is a positive side, and the other one's back side will be it is a negative side. Okay, similarly for the case of fuel cell, it is also, it will be the one positive and one negative, but it is a open system. Okay, in the battery completely is closed. Okay, in the fuel cell it will be the open system. This concept is also similar to the fuel cell concept. It is also one type of the open system. So it has the two side. One is it is a positive side, another one will be the negative side. So then what will be the difference between the microbial difference between the fuel cells and the battery? Okay. So in the fuel cells and battery is nothing but it's a fuel cell. It is also chemical energy converted into the electrical energy, and a microbial fuel cell is also converting the chemical energy into the electrical energy. Then what will be the difference is that in the fuel cell generally any kind of the process, either the battery or fuel cell or microbial fuel cell, it needs catalyst. Okay, it needs the catalyst. Without the catalyst it cannot work. Okay, so one simple example I will tell you this. We have the hydrogen, we have the oxygen. Okay, if it reacts together, okay, hydrogen and the oxygen, it has to form the water molecules. Okay, H2, if you are chemical engineering or if you are biotechnology, you know that physics also, H2 plus O2 gives H2O. It has to form H2O, but whether it will form or not, it's supposed to form H2O, but it will not form immediately. Okay, so it will take nearly 100 years to form the hydrogen and oxygen, form the water molecules. But at the same time, if you use the catalyst, okay, so for example like a platinum catalyst, if you put it in that, okay, which in fraction of second or micro fraction of second, it will convert into the water molecules immediately. Okay, it is a one type of reaction. It may be the exothermic reaction, so it is also generating the heat also. Okay, so it may be depending upon the catalyst, what type of catalyst involved in this process. So it forms the water molecules either the immediately or it is a slow process, depending upon the catalyst. Okay, then now come to that point. So as I said, it is a fuel cells and the battery fuel cells and the microbial fuel cell, both are in the same concept I told you. So it's a fuel cell, we need the platinum catalyst. So microbial fuel cell, we have the what, microbes as a catalyst. Okay, microbes as a catalyst. So here bioelectrochemical system, so which converts the chemical energy into the electrical energy. So here we have microorganism will be in the one side, that is the anode side, and the second side will be the negative, that we will see will be the, it is a cathode side. Okay, it is bioelectrochemical system. It has the, it is one type of system which is anode and the cathode. These two are separated by the membrane. Okay, any separator, or we call it a separator, or it is a cation exchange membrane, I will call it as PEM, that means it's a proton exchange membrane. Okay, so what will happen will be in the anode. So in the anode, so what are the wastewater? Okay, wastewater available in the open source, that it will be put it in the anode side, that anode degraded by the microorganism. So the microorganism will convert the organic matter into the carbon dioxide and the H plus ions and the electrons. So these electrons will move through this external circuit to the cathode, where the cathode combined with in the cathode side, this electron will come, and the again the cathode side, these protons, okay, these protons are generated in the anode side, that proton will move through this membrane. Okay, it's a one type of separator. Okay, it transfer the protons. Okay, transfer the protons to the one side, to the, that is anode side, to the cathode side. So cathode side, now it is the electron also has come to the cathode side, and the protons also has come to the cathode side. So now the electron is there, proton is there, and again we have the, in the cathode side, oxygen will be there. So oxygen and the protons plus electrons combine to form the water molecules. At the same time, it is producing the electricity. Okay, this is the concept of microbial fuel cell or bioelectrochemical systems. So here we can say it is how that your the process is taking place. Okay, so as I said, in the anode side we are taking the wastewater in the anode side. So the microorganism degrade the organic matter, isn't it? So once the microorganism degrade the organic matter, what will happen in that? It produces the oxygen. So it produces the carbon dioxide and the electrons. So electrons are produced. So how that electrons are transferred? Okay, that is the most important. So here there will be two methods. One is the direct electron transfer method, another one is the mediated electron transfer method. So As I said, microorganism play a major role. Microorganism only act as a catalyst. Okay, so it degrades the organic matter. So it is all the microorganism cannot say it will degrade the organic matter. Okay, so even if it degrade, it has to transfer from the one side to the another side. Okay, so all the microorganisms will not have the same capability. That means it transfer from the one side to the another side. So based on the transformation, we can classify in two types. One is direct electron transfer, and the second one is the indirect electron transfer. Okay, indirect electron transfer. So that is in the direct electron transfer, there will be two method. One is it will be the, so here you can see this, it will be the one, we can call it as nanowire. Okay, it's nanowire. Wire this, once it degrades, immediately it can transfer to this nanowire, one end to the another end, it will be transferred. But as in the case of second one, it will be conductive pili. Okay, or we can say it's a nanowire. So here you can see it. So here this your degradation process is taking place. So once it's degraded, so it will transfer through this nanowire. Okay, through this nanowire, and it goes to the anode electrode. It goes to the anode electrode. So some cases, what will happen? So this process will not take place. Okay, we need to add some kind of the mediator. So here, what happens in this? Okay, it cannot. So it is, once its electrons are generated, these electrons are transferred from this to this side. But here you can see it. It will not happen like this. So in that is the case, we need to add some kind of a mediator. That is called, it's an indirect electron transfer. Okay, so that it will transfer the electron with the support of some kind of a mediator. Either it may be the chemical mediator, it may be the another kind of the mediator. So while adding the mediator, here you can see it is, here it is electrons are generated. This electron will move with the support of media. Okay, support of some kind of the mediator, that's electron shuttle. That electron shuttle will help to transfer the electron from this these two electrode side. Okay, these to the electrode. So depending upon the what kind of the mediators you are using it, and whether it is electron transfer, it's a fast or it will be slow process. Okay, depending upon the what type of mediator. So here here we can see it, there will be a different kind of the microorganism. So here we have the wastewater. So wastewater contained n number of microorganism. Okay, n number of microbes will be in this wastewater, depending upon the what type of microbes involved in the process. Okay, so here one of the example is E. coli bacteria. Okay, our surrounding environment, we have the E. coli. So if you see it, you can see one day, once you cook the today, okay, if you keep it that that cooking product, if you keep it in the next day, so it will be spoiled. Okay, why it's spoiled? It's because of the bacterial action. Okay, it is a, we have this in the surrounding environment, we have the all kind of the bacteria like E. coli bacteria, or some other bacteria will be there. So because of that reasons, it is that your food product is going to be spoiled in the next day. Okay, because of the bacterial action. So here you can see it is depending upon the what type of bacteria involved in this process. Okay, one of the example is E. coli bacteria. Okay, if you take the E. coli bacteria, so if your wastewater contains glucose, okay, wastewater means is a, for example, domestic wastewater. So we are taking the, is a carbohydrate. Carbohydrate is a one type of glucose. Okay, isn't it? So if you see it here, you can see if a wastewater contains glucose, so it shows the potential of 625 millivolt. 625 millivolt is produced. At the same time, here you can see the same glucose, but you have different bacteria. Say bacillus, is another type of bacteria. So, but it shows the potential will be the 645 millivolt, 640 millivolt. Same as it is. That is here, same E. coli bacteria, but your wastewater contain, instead of glucose, it contains some kind of the starch or some kind of the protein rich materials in this. So it will show the different potential. Okay, depending upon the what type of species involved in this, accordingly it generates the different potential with this. Okay, now here you can see it will be, okay, so now you see, so how that voltage calculations and how much voltage will produce in the single cell or in the systems. Okay, so suppose this is one of the reaction. Okay, in the anode side what will happen, and the cathode side what will happen. Here in the anode side, if you see it, suppose your wastewater contain acetate. Okay, if it has acetate, if it is acetate, so it forms this 2 moles of CO2 and 8 protons and 8 electrons will produce if wastewater contain acetate. Okay. Similarly, if the wastewater contain glucose, so it shows that 24 electrons. Okay. It produced 24 electrons and 24 protons. So 6 moles of carbon dioxide. Okay. 6 moles of carbon dioxide. So this is a reaction will take place in the anode side. Similarly, in the cathode side, if you see it, so here in the cathode side will be the oxygen. Okay, in the oxygen, in the so as I told you, in the whatever the protons are generated, that proton goes to the cathode side, and similarly electrons also goes to the cathode side. It will be the protons and the electrons. If you use the oxygen here, that 4 protons and 4 electrons will combine. Okay, so it forms the water molecules. So similarly, instead of oxygen, if I take the another kind of the electrolyte, okay, electrolyte. So like we can take other electrolyte like potassium ferric cyanide and potassium permanganate and potassium chromate. Okay, depending upon the reactions. Here you can see. So if I take the potassium ferric cyanide, so it convert into the ferric cyanide into the ferrocyanide. Okay, ferrocyanide. Then how this is a reaction? This is a reaction. So how we can calculate the potential with each side? Okay, this is a reaction. So here you can see it is a standard electrode potential. Okay, standard electrode potential. It is nothing but it is a which will be equal to minus delta Gr. Okay, delta Gr means it is a Gibbs free energy for the reaction. Gibbs free energy for the reaction, and where N will be the number of electrons and F will be the Faraday's, because it's an electrochemical process. It will be the Faraday's will involve in this. Okay, Faraday's constant we have to include in this. So as you know this, it is a Gibbs free energy for the any kind of the material. Okay, it is available. Standard material is available in the literature. You can find out. Okay, if it is acetate or if it is glucose or if it is fructose or if it is lactose. Okay, all the materials will have the some Gibbs free energy value. Okay, so and here you can see one type of one example, like if I consider the glucose. So here this how many electrons? That is 24 electrons. So here we need to add the how much N? N will be the 24. And then Faraday's constant, it is according to the Coulomb's law. Okay, we have to check the Coulomb's law. So Coulomb's law will be the 96,500 coulombs per mole. And similarly, we know the glucose, what will be the Gibbs energy for the reaction. So if I put it in this, so you will get it this much potential. Okay, it will be the minus 0.428. So because of it is releasing the electron. Okay, it is releasing the electrons. So your values will be the negative. Okay, negative. Same as it is when you go for the another side in the cathode side. So it is accepting the electron. So it will be the positive value. Okay, here you can see. We take the oxygen. It will be that same way. If you calculate it, you will get it positive value. So 0.816. So now, so we have considered the one side will be the anode, one side is the anode side and the cathode side. So what will be the cell potential? So cell potential means it is the difference between the cathode and the anode. So if I put it this one, like in the cathode side, if I consider the oxygen, so it will be the it will be the 0.816. In the anode side, it will be, if I consider the glucose, okay, it will be minus 0.428. So now what I have to do, it is a difference between this one. So 0.82816 minus of minus 0.428. Okay, it will show, it will give that 1.21 voltage. So one single cell can produce the maximum potential of, it is a 1.21 voltage. Okay, got my point? So it can produce 1.21 voltage. Even any cells if you consider. Okay, so you are using the battery. Mobile phone, you are using the battery. Anybody have seen this? What is the voltage of the battery? What type of batteries you are using it? Huh? It is a lithium ion battery. It will show the 3.6 voltage. So it is a single cell or multi cell. Huh? How we are saying this is single cell? Have anybody is in your home you would have seen this UPS. It is a 12 volt battery. How many batteries will be inside? Have you seen that? Anybody? Huh? There will be a 6 holes will be there. How many batteries will be in this? Depending upon the what type of electrode, okay, what type of battery you are using it. Either a lead acid battery or it is a lead acid battery or lithium ion battery, okay, depending upon that. Okay, your mobile phone you would have used lithium ion battery. Okay, lithium ion battery, it may be voltage will be 3.6 something will be there. Okay, just check in your mobile phone. Okay, so it depending upon that. So now you see, so as I said, there will be it's a single cell can produce the maximum voltage of 1.2 voltage theoretically. Okay, because we have taken the reaction. So what will happen will be the anode, and what will happen will be in the cathode. So difference between the cathode and the anode, it will show the cell voltage. Okay, now 1.2 voltage must show in that your cell. If you have the multimeter, if you take the anode side and if you put your multimeter, the positive and negative terminal in the anode and the cathode side, it has to show the 1.21 voltage, but it will not show 1.21 voltage. Okay, it will give the that cell itself having the some losses. Okay, that losses are, there will be a, because here lot of things is happen. Okay, isn't it? So one is the biodegradation is taking place. The another side the reaction is also electrochemical reaction is also taking place. Okay, so each side will be the some losses will be there. So that losses are, we can say it will be we can say three type of losses in this. One is the activation losses, and the second one will be the internal resistance losses, and third one will be the we can say internal resistance losses, or we can say it is a ohmic losses. Okay, and third one will be the concentration losses. Okay, concentration losses. The first one will be the activation losses. So what is meant by activation losses? So we are using the catalyst. We are using the catalyst. So catalyst immediately it will start the reaction. It will not start the reaction immediately. Okay. So let us take, you are in the marathon, in the marathon ground. Okay. So it will be the either 15 kilometers or 20 kilometers. We have to run. We have to run fast. Okay. If the starting itself, if you run fast, so at the end of the end stage, we cannot run so quickly. Okay, it will be you will lose the energy. Similarly, so here also, so what will happen? While the reaction is taking place, it will, that cell itself, it will lose some kind of the energy. Some kind of the energy. That is called activation losses. Okay, so it is any reaction needed activation energy. That activation energy will give that. Okay, due to the activation energy needed from any kind of the oxidation or reduction reactions. But so these kind of the losses, okay, suppose here it will give the 1.21 voltage, single cell will produce 1.21 voltage. Okay, so if it is not activated, your cell, if it is not activated, so if it is not activated means that if catalyst is not working, it will not generate the voltage, it will not produce the voltage. Okay, but the possibility is there, so we can minimize that losses. Okay, activation losses we can minimize it. How the way we can minimize it is that, one is that, so we have to boost the reaction. By boosting the reaction means we have what we can do, we have to enhance the surface area of the catalyst. That is one point. Or we have to like boost the your microbial activity. We have to enhance the microbial activity. Via this we can minimize the activation losses. So second one will be the ohmic losses. So ohmic losses is nothing but it is the we can say ohmic losses are internal resistance losses. So ohmic losses or internal resistance losses is nothing but, so as I told you earlier, that is anode side the protons are released. That protons will move through the membrane to the cathode side. That movement of protons from the one side to the another side, if it is restricted, there will be no reaction at the cathode. Okay, no reaction at the cathode. So how to minimize that losses? So here this is our cell, here this is our cell. So we have these two electrode, this is the one electrode, this is another electrode. Okay, so once the protons are generated, that proton will move through the membrane to the another side. So if I keep it close together, so it will move fastly. If I keep it long distance, okay, it has to transfer too much time, too much distance, then it has to go to the another side. So that movement of transfer of proton from the one side to the another side, okay, it creates some losses to the cell. So to avoid these losses, we have to keep the electrode to be close to each other. Okay, that's the one aspect. Another one is that we have to either enhance the or either increase the electrolyte conductivity. Okay, if there is no conductivity, then your protons will not move from the one side to the another side. Okay, that losses can be minimized. Second one, and third one will be the concentration losses. Okay, so what is the concentration losses? Is that here you can say resistance to the flow of electrons through the electrodes and interconnections, that is a concentration losses, or we can say it is a mass transfer losses. So suppose here whatever the electrons are generated, electrons or protons are generated, that protons and electrons must be combined in the cathode side. Okay, if 10 number of protons are generated in the anode side, 10 number of electrons will be in the anode side, that all the 10 must be transferred to the cathode side. Okay, so it has to accept cathode side, 10 electron must be accept. Suppose that cathode side it is having the capability of only 10 electron acceptance, but anode side generating 100 electrons and the 100 protons are generated, but your cathode side it is having the capability of accepting only 10 electrons, remaining 90 electrons is not going to be utilized. Okay, how to, that is the one type of losses, that is called is concentration losses. Okay, to minimize that, what I have to do, I have to enhance either the anode side, so cathode side, I have to boost the bireaction. Okay, if I boost the bireaction, then automatically whatever the 90 electrons are produced, that 90 electrons will be accepted by the cathode side. Okay, so as I told you, there will be three losses. One is the activation losses, and the another one is the internal losses, and third one will be the concentration losses or mass transfer losses. So we can say it's based on this. Here we have the one graph that is called voltage versus current density graph. Okay, so y axis will be the voltage and the x axis will be the current density or current. So while taking the load, okay, while taking the load, so as you know this, y will be a function of x. Any equation mathematically, if you see it, y will be a function of x. Okay, that x profile may be either the linear or non-linear or exponential, whatever it is. So my y will be depending upon the x. Okay, depending upon the here how much load, that is how much current you are drawn from the system. Okay, accordingly that voltage drop will be there. Okay, this is the first drop. Okay, so here we have the we can say three categories. That is this is the one first one, that is called activation losses. Okay, activation energy losses. This is second part. Okay, this it will be the second part. It will be the internal losses, that is the internal resistance losses. This is second part, and third part is the it will be the concentration losses or mass transfer losses. So according to this equation, so as I told you, there will be a single cell can produce the potential of 1.2 voltage. 1.2 voltage, while starting itself it will show the some losses, that is activation losses. Then again while taking the current or load, so again some losses will be there, and if you take the too much current, too much load, then heavy loss will be there. So theoretically it can show the potential of 1.2 voltage, but experimentally if you go that system, it will show the maximum potential of 0.8 to 1 volt. Okay, it will show 1 volt, and after taking the load, again it will drop to 0.8 to the 0.2 voltage. Okay, so nominal voltage for the single cell it will be 0.6 voltage, 6 to 8 voltage depending upon that. Okay, nominal voltage. If you take the load, okay, this is a region. Okay, up to this we can take the load. Beyond this, if you take the load, so your cell will lose the activity. Okay, so one of the simple example, Like in your inverter, you would have seen your hometown, you may have the inverter. They would have told you that this many fan, this many light you have to switch on. Okay. Generally, what we'll do, if it is your inverter or your battery can give the 1 kilowatt. 1 kilowatt means, so as per the vendor will say this, you cannot take 1 kilowatt. You can take nearly 500 watt. You cannot go beyond that. Why they are saying this? We cannot go beyond, because as per this specification, it can give the 1 kilowatt. But the vendor is saying that it can take only 500 watt. So even if you go for the 700 watt, it will work or not. Definitely it will work, but stability of your system will lose. Okay, so 1 kilowatt UPS, if you are using it, it has to produce, we have to run up to 500 watt. Beyond that, if you run, it will work, but short duration, only very few duration. Okay, it will go to the your cell voltage, your cell will become damaged. Okay, it means the damage means it's in the form of, it will create negative potential. Okay, if it goes to the negative, cell voltage goes to negative, again it cannot regenerate back. Okay, minimum of 50 times or 100 times it can regenerate. Beyond that, it will not regenerate. Okay, it will lose their activity, or it will lose their lifetime. Okay, over the short period of time itself. Okay, so that is called, that point is called is a cell design point. Okay, cell design point means it is nothing but it is the critical point where the peak power density obtained by the system, where the peak power, okay, maximum power can be obtained. So as I said earlier, that is this 1 kilowatt system means we can take 1 kilowatt, but we cannot run the system with 1 kilowatt for the longer time. Beyond that region, we have to run the system. That is called is a cell design point. Okay, any critical point will be there for the any kind of the electrochemical systems. Okay, similarly for the microbial fuel cell also. Now, you see, so as I told you earlier, like microbial fuel cell is a one type of systems, that is it can be it can use for the different things. One is the energy production, at the same time it's a treatment. One is for the treatment. So performance of microbial fuel cell means we have to say the two aspects. One is the how much amount of the energy is produced, first one, and the second one will be the what will be the treatment efficiency. Okay, so treatment efficiency means, here we will say the treatment means in terms of removal of COD. Okay, COD means it's nothing but it is a chemical oxygen demand. Okay, what is chemical oxygen demand? So chemical oxygen demand means it's maybe such scholars may be knowing this. Some kind of the BTech students is also attending this workshop. Okay, they should know that. Okay, it's a chemical oxygen demand is nothing but it's a how much amount of oxygen is needed for oxidizing the organic matter. Okay, oxidizing the carbon in that. Okay, carbon content in the waste, that is called it is a chemical oxygen demand. Okay, so chemical oxygen demand we can measure in terms of two way in terms of closed reflux method or titration method. Okay, titration method. So here in the titration method we need to use the two kind of the reagent. Okay, one is the acid reagent, another one is the, what is that? There will be two reagent. One is a sulfuric acid, another one is a mercury sulfate reagent. Okay, so that is a silver sulfate and the mercury sulfate and the sulfuric acid. So these three chemicals will be involved in this process to find out the what will be the chemical, what will be the COD value of the systems. Okay, so it has some norms. Okay, as per the standard norms, we can find out the what will be the COD removal and all. Okay, so now you see performance of MFC. Okay, it is what is the voltage, as I told you. Now how the voltage we can measure from the systems. Once you measure the voltage, so we can find out the how much power is produced from the systems. Okay, so power, we can use the power calculation, we can use the Ohm's law equation, simple Ohm's law equation. Okay, so as you know this Ohm's law, which will be V equal to IR. It's a Ohm's law equation. Okay, so simple equation. Once you find out the current, we can calculate the power also. So power, we should know this. Power will be P equal to I into V. Okay, current into the voltage will be the power. Okay, so here we will measure the power current in terms of power density or current density. Okay, so because it's an electrochemical process, electrochemistry process, so it depends upon the area of the electrode. Okay, what area of the electrode you are using in the system, so accordingly it will generate the power. Okay, so generally we will calculate is a power or power density. Okay, so power density or current density, which will be based on the electrode area. If we see the anode electrode area, it will be the power per unit area of the electrode. Similarly, cathode means power per cathode area of the electrode. Okay, or if we take in terms of volume of the electrolyte, so that also will be called as power density or current density. If it power density means power per unit volume of the electrolyte. Okay, this is one. So once you find out this one, and the second one will get it, this COD, the mole efficiency. As I told you, like if you start the process, what will be the initial COD you consider? At the end of the process, what will be the COD? Okay, so difference between the initial COD and the final COD divided by the initial COD, if you put it, you will get the what will be the COD, the mole efficiency. Okay, this is one. Then next one will be this is the most important one, is the Coulombic efficiency. So Coulombic efficiency is nothing but it is so how much amount of the chemical energy is converted into the electricity. Okay, how much amount of the chemical energy is converted into the electricity. It means that, so as I told you here, we are using the bacteria. So bacteria is act as a catalyst, isn't it? Okay, so the bacteria, it needs some energy for their survival, isn't it? So bacteria has to consume some kind of the energy for their growth. Okay, then only it can release the electrons. Okay, some amount of the energy can be utilized by the bacteria, some amount of the energy the bacteria can convert into the electricity. Okay, that is how much amount of the energy is available in the substrate, available in the wastewater or substrate, and how much is converted into the electricity. Okay, that is called Coulombic efficiency of the system. So you can see here it is how much here you can see, as I told you, like for the particular period of time, delta COD, that is change in COD for the particular period of time. Okay, then here integral of 0 to TB, so that is how much time you are running the system. Okay, if it is 1 day, so 1 day means 1 day you are running the system means, so what will be the initial COD, what will be the final COD for the 1 day it is consuming, and what will be the current you are taking from the system. Okay, how much volume of the your substrate you have taken in this system. And the other thing, if you calculate, it will give the Coulombic efficiency. So another one is energy efficiency of the system. So energy efficiency is nothing but it is how much amount of the power is produced by the cell and how much amount of the energy available in the system. Okay, available in the system. That is call it as energy efficiency of the system. In addition to that, some kind of the other factors also, if it is there. Okay, suppose if I take the wastewater, if I take the what I can say is a ternary wastewater. Okay, so ternary wastewater or ternary wastewater is contain lot of salt will be there. Okay, the salt removal also we need to account in this. Okay, that is called, it is a desalination efficiency, that is salt removal efficiency. It's nothing but it is a ratio of, it is a difference between the change in salt difference divided by the initial salt, how much is available. Salt removal efficiency. Then color removal efficiency also. If you take the dye industry wastewater, so initially what will be the color and what will be finally what will be the color divided by the initial, if you consider, it will give the what will be the color removal efficiency also we can find out with this. Okay, these are, it will be the important parameters to measure the performance of bioelectrochemical systems or microbial fuel cell. Then then this is one of the important. So what will be the strength and the weakness of bioelectrochemical systems? Okay, so as I told you, the bioelectrochemical systems mainly used for the two purpose. One is the removal of pollutant. Okay, removal of pollutant from the wastewater, that is one of the advantages. And the second one will be the to get the energy, to produce the energy from the system. Okay, these two are main advantages, but at the same time it has some of disadvantages also, and it has some kind of the, in addition to the some of the advantages also. So like one of the disadvantages is that it's not disadvantages, you can say, as I told you, so a single cell can produce the maximum potential of 1.2 voltage. So experimentally if you consider, it will show the 0.8 voltage. Okay, so our mobile phone cell, okay, we have the battery, okay, that needs 3.6 voltage, but this cell can produce the maximum potential of 0.8 voltage. What is the use of this system? This system, nothing. We can say nothing, but I will say it's not nothing. So it has some solution. Okay. So as I told you, single cell only can produce the maximum potential of 0.8 voltage. If I connect n number of cells in the series or parallel, okay, so I want 3.6 voltage. Single cell is producing the 0.8 voltage. If I connect 4 or 5 cells in the series, I can get the 3.6 voltage. Okay, 3.6 voltage I can get the energy. I can get the power for the my mobile phone. It's a simple example. Okay, so single cell can produce the maximum potential of 0.8, but that's if I want to go for the real time applications, so I have to connect n number of cells in the series or parallel, okay, to get the energy for the real time application. That is one of the advantages. And the second one will be the, as I told you, it is here it can able to produce only the electricity. Okay, not only the electricity, it can also able to produce some kind of the value added product also. So that one is, instead of electricity I can produce a hydrogen, or I can produce the some kind of the other value added product, means like I can produce the ethanol, or I can produce the methanol, I can produce the hydrogen peroxide, and many things I can produce via this system. And I can use this system as a sensor for monitoring the glucose level of our body. Okay, that we can do with these systems. So, but it has some third domains like it has some thermodynamic limitations. That is the first one, and one of the weakness of the system will be, as I told you, like it has less energy. Okay, less energy is produced as compared to the other kind of system like fuel cell and all. Okay, but it has a lot of opportunities in this. Then next one will be the, so what are the components involved in the microbial fuel cell or bioelectrochemical system? So there will be a 3 component mainly involved in the bioelectrochemical system. The component 1 will be the anode, component 2 will be the cathode, component 3 will be the, it is a membrane, okay, or separator between the anode and the electrode. So why need of component, that is anode component and cathode component and the membrane, okay, that we will see it. So what is the importance of anode? So as I told you, so we have the wastewater in the anode side. That wastewater will be the degraded by the microorganism. Once it's degraded, that electron must be transferred, okay, from the anode to the cathode. So it cannot transfer directly. It will transfer with the support of one source, okay, one material, that is called electrode. Okay, anode electrode. That's called anode. If you use the electrode in the anode, it will be the anode electrode. If you use the electrode in the cathode, it will be the cathode electrode. Okay, so anode electrode should have some important characteristics. So what are the important characteristics is that, so whatever the electrode you are using in the anode, okay, it should be biocompatible. It should be familiar, or it should be compatibility with the microorganisms used in the system. That is one of the important. Okay, second one will be the, it is a surface area. It should have highest surface area and its porosity, and third one will be the, it should be the highest electrical conductivity, and fourth one will be the, it is a, the material should be, that electrode should be very cheap. Okay, very cheap, that material should be used in the systems. Okay, so one important point is that like as I told you earlier here, that electrical conductivity must be high. Okay, electrical conductivity must be high. Suppose we have the two material, like we have the copper material, we have the stainless steel material. So which one we have to use it in the systems? So copper will have the highest thermal conductivity, highest electrical conductivity, and SS as compared to the copper, it will be less. Okay, which one we have to use it? Which one we have to use it? Either the copper we have to use it, or we have to use the SS material. Okay, so you can say we can use the copper, but I can use, but SS will be the costlier than the copper, no? Pardon? SS will be the costlier than the copper, but copper has the highest conductivity as compared to the SS. But our concept will be the SS should be the highest conductivity. So if I use the copper in this, copper will be the highest conductivity, because if I have the highest conductivity, then only the electron transfer will be smooth, isn't it? But if I use the copper in this, then what will happen? Here it's my electrolyte will be the water, wastewater, isn't it? So over the period of time, what will happen? The copper will get corroded. It will form the copper oxide. So over the period of time, it will lose their activity, isn't it? Okay. So I cannot use the copper. But at the same time, if I use the stainless steel, I can use it, but it's expensive. So depending upon the lot of things, we need to consider based on the availability and based on the materials conductivity and other aspect also. Okay, we'll stop it here. Okay, we'll stop it here. We'll have the break. Then after that we'll start. Okay, I think what's the time now?